Today, we tackle a problem involving multiple string shifts. Imagine a string and a series of instructions to rotate it left or right by various amounts. The challenge is to determine the final state of the string after all these operations are applied. You are given a string and an array of shift operations. Each operation specifies a direction, either left or right, and an amount. A left shift means removing characters from the beginning and appending them to the end. A right shift means removing characters from the end and prepending them to the beginning. Your task is to return the final string after all operations are performed. A straightforward approach is to simulate each shift operation one by one. For every shift instruction, we can slice the string and concatenate the parts to achieve the rotation. For example, a left shift of an amount would take the first amount characters and move them to the end. While simple to understand, this method can be inefficient. Each string manipulation can take time proportional to the string's length, and if there are many shifts, the repeated string copying and building leads to a time complexity of O, n asterisk m, where n is string length and m is the number of shifts. Space complexity is big O of n due to new string creation in each step. The key insight for optimization is that the individual shifts don't matter as much as their cumulative effect. Instead of performing each shift, we can calculate the net shift. Think of a left shift as a negative amount and a right shift as a positive amount. We iterate through all the operations, accumulating the total shift amount into a single variable. After processing all operations, this variable will hold the net shift. Since shifts wrap around the string's length, we take the modulo of this net shift with the string's length. If the net shift is negative after the modulo, we adjust it to be positive by adding the string's length. This final, adjusted net shift tells us exactly how many positions the original string needs to be right shifted to reach its final state. We then perform this single right shift by splitting the string into two parts and concatenating them. Let's trace this with an example, string ABC and shifts of left 1, then right 2. Initially, our net shift is 0. The first operation is a left shift of 1. We treat left shifts as negative, so net becomes 0 minus 1, which is minus 1. The next operation is a right shift of 2. Right shifts are positive, so net becomes minus 1 plus 2, resulting in a net shift of 1. Now, we've processed all operations. The string length is 3. We take the net shift, 1, modulo the length, 3, which is still 1. Since it's positive, no further adjustment is needed. A net positive 1 shift means a right shift of 1. We take the last 1 character, C, and place it at the beginning. The remaining, AB, follows. The result is cab. The final string after all shifts is cab. This is correct because a net rightward shift of 1 position from ABC directly produces cab, consolidating all the intermediate operations into one final movement. You'll spot this pattern whenever you see multiple operations that accumulate or cancel out on a single entity, like a string or an array. Specifically, if the operations are commutative or if only the final state matters, calculating a net effect is often the optimal approach. This is common in problems involving rotations, sums, or transformations where intermediate steps can be aggregated. The time complexity is O, n plus m, where n is the string length and m is the number of shifts, as we iterate through shifts once and perform one string operation. Space complexity is big O of n for creating the final string. Try the next problem on string rotations, same pattern. If you found this helpful, subscribe for more concise DSA explanations.